everyone, this is KP the Math G here, and I'm here to talk about the big three in AP Calculus. What I'm saying here is that I have been doing videos from free response questions. Most of them have been free response questions, and I'm on the verge of getting 200 videos done. I want to say this will be the 198th video that I do, and all of these have been calculus based. So what I want to do is I'm going to go over 200 videos. Where I stop, I don't know. 205, 210, who knows where I stop with this. Well, what I want to do is I'm not going to do awfully too many more. What I'll do is I'll probably get into ACT stuff, SAT material, and maybe even some college algebra, maybe some algebra 2 or whatever, trigonometry, pre-calculus, whatever I do. I just want to, everything's starting to, it's been overlapping for some time, and maybe a little angle that's a little different from one other problem, but by and large you're getting the same problem. So instead of doing that, especially if you are a beginning AP student coming up this year, this will benefit you tremendously. Let me say it again, tremendously. Okay, so what I want to do here is talk about the big three, and I'm just going to relate to them very quickly. There's the limit, derivative, and integration. That's the big three. We're going to begin with limit, and then we'll go to derivative and then integration a little bit later. This entails a lot of work here. So, in other words, several concepts that go with the limit. In particular, what we're going to get to, the limit is going to lead us to the derivative, but even before that, we're going to talk a little bit about continuity. Okay, when we get to limits here, but let's get into the limit for now. So I'm going to erase these other two, but those are the big three. Okay, now let me see if I can find, I'm getting where these markers are not writing as clearly as I'd like for them to do. So I have actually come up with several pages. I'm actually on about page 4 or 5, but that's going to be several lessons in and of themselves. So I imagine probably at least 8 or 10 more videos, maybe more, okay, that deal with all of the three. So let's talk a little bit about limit. What is a limit? Okay, so what we're saying is that the limit of a function, say maybe if I come up here and I stop here, and this happens to be 5, and this happens to be maybe 6, the limit as x approaches 5, let's call this a function of f. F at x is 6. That's the y value, okay? And that's what we're talking about there. This could go on, okay? But the limit there as x approaches 5 is 6. Just like that. And that's what basically the basic idea behind the limit is, okay? Alright, it's that y value. Okay, so let's talk about it. Let's do some algebraic problems. let's find the limit, and the limit is given by LIM. Okay, and we're going to do as x approaches 2. I made up these problems myself, so I just wanted to tell you what you can do with limit. Okay, 3x squared minus 4 over x plus 2. What you want to do is you want to make sure that if you have a quotient like this, sometimes you don't have a quotient, but sometimes you do. Oftentimes you do. If you plug 2 in right here, 2 plus 2 is 4. You do not want your denominator to be 0. Had this been minus 2, then we couldn't do this. Okay? And there's cases where, in this particular case, the limit does not exist. But it does. All you got to do is plug it in. So in other words, the plug-in method, if you plug in the denominator, you got something other than 0, then just plug it in now. So this is equal to the limit as x approaches 2. Move over here, 3 times 2 squared minus 4 over 2 plus 2. 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. I want to say that's equal to 2. 2 squared is 4. 3 times 4 is 12. 12 minus 4 is 8. 8 over 4 is 2. So the limit as x approaches 2 of this f, we'll call it f or g or whatever, the answer is 2. And there it is. I got it. Yep. Alright, sometimes you just plug it in. So that's what I'm saying. Alright, let's look at another limit. Bear with me. I could keep going on down, but I'm just going to try to stay on one side of the board if I can. Sometimes limit is called what we call removable. In other words, we may have to factor something out. X minus 2, and I'm thinking that this is yes, and again I could have left this x approaches. This means as x approaches. Okay, limit as x approaches 2. And later on when we talk about approaching x from the left side, approaching x from the right side, do they coincide or do they differ? Alright, if they differ, the limit does not exist at that number. Okay, so we'll talk a little bit about that later on. Now I think what I have here is x squared minus 4. That's correct. You see now if we plug 2 in and square it, minus 4, we got 4 minus 4, we got 0. And there's a couple ways we could handle this, but I'm going to show you the simplest way. Alright, well I say it's the simplest way anyway. One of them is called L'Hopital's rule. Okay, if a numerator and the denominator both give you 0, you can apply L'Hopital's rule. There are other cases where you can apply L'Hopital's rule, but in this particular case you can. Some cases you cannot. And I will get into L'Hopital's rule a little bit later when we get into derivatives. But right now you can just factor. I can factor x squared minus 4. Probably you saw that. Alright, now we know that's the difference of two perfect squares. X plus 2, x minus 2. Notice here you got something that you can cancel out. Do not leave it as just x plus 2. That's 1 over x plus 2. Sometimes we make mistakes doing that. It is common to see that sometimes, but don't do that which is common to see. Put a 1 up here. There is something here. It's 1. Alright. And we're saying that as x approaches 2. We're not saying that x is equal to 2, it's approaching 2. We can still cancel it out. I know that if you plug 2 in, that would be 0. But there again, it's approaching 2, so you can cancel or divide these out. Now I can plug 2 in. Now I can just simply put 2 plus 2, and now that's 1 over 4. And there it is. So sometimes you have to factor. Okay, sometimes you don't have to factor at all. Had this been a plus 4 right here, you could have just plugged it straight in. Would have been 0, because 2 minus 2 is 0. And then 2 squared plus 4 is 4 plus 4 is 8. So 0 over 8 would have been 0. So this, but we couldn't put it in as it was. We had to factor. We had to get rid of that. This leaves a hole right here at x equals, I want to say at x equals 2. This is a hole right here. Wherever the graph is, in other words. So here's 2. Wherever it is, there's what you call a hole right there. Okay, well, I don't know what that looks like. I'm just saying, if that, just giving you an idea of what the graph would look like right there. There's a hole. Okay, it's not solid through and through. Okay, I don't have a picture of that graph, but I could do it and I'll show you. But anyway, this is the idea. This is all we're doing. We're doing it algebraically. We're not doing anything graphically yet. Okay. So sometimes you have to factor. Okay. Now, sometimes, let's see if I can get to the limit again. Now, sometimes we have limits of infinity. Okay. And sometimes there's a negative infinity, sometimes there's a positive infinity. We're just going to use positive infinity for the time. We could have done negative just the same. Oh, infinity. Okay, so what happens when x approaches infinity and we got something like this? 2x over x plus 3. Oh boy, infinity over infinity, right? You can keep going over and over and over, right? But the idea behind infinity is to do something like this. We can manipulate the problem, we can change it. So here's what happens. I'm going to show you, let's say you have something like, oh, I don't know, 5 over x. I'm just going to give you this one. Now, this is different than this one, I know. But as x gets larger and larger, so if you put 1 here, it's 5. If you put 2 here, it's even smaller. 5 over 2, half of 5. You put 3, it's a third of 5, right? You put 5 in here, it's 1. And you keep going, and it's 1 smaller from 5 to 1, right? Now, if you put something larger and larger and larger, it's going to keep getting so small that this, like 5 over a bunch of zeros here, like this, okay, 5 over a million is very small. So what happens is, what we say about this is, this eventually leads to 0. It gets so small that we just say that limit is 0. So just keep that in mind. You got x in the denominator. The bigger that denominator gets, the smaller the number gets, and the smaller this numerical value gets. So what happens is, it eventually leads to 0. So here's what we're doing. I want to show you what we can do here. Alright, so we've got the limit as x approaches infinity. Alright, so I'm going to have 2x, and I'm going to put the numerator over x, and then I'm going to say, let's see how I want to do this. 2x over x over, I can actually do this, the limit as x approaches infinity. Okay, x over x. I'm just dividing everything by x, right? Alright, the numerator is divided by x. This denominator here is divided by x. And I can do the limit. There is a rule that says that we can distribute the limit over all the terms. So we're just dividing by x. Now we know x cannot be 0, otherwise this is meaningless. But notice here that this is x over x, this just leaves 2. So this answer up here in the numerator is just 2. This answer right here is 1 over 1, which is just 1. And then we got a plus. Now this, we did the 5 over x like that. That limit so small. Remember that the bigger this number is, the smaller it gets. So it's 0. So this limit is 2 over 1, which is 2. Okay. And that's, you know, that's pretty much what you have with these exponents. Now you learn from the, and this is actually one way to find, in this particular case, in this case, we can find what you call a horizontal asymptote. You have a horizontal asymptote at x equals 2. Your vertical asymptote is -3. What makes this denominator 0? But that is what you can do to find the vertical asymptote, and in this case it is at 2. Okay, like that. Again, just simply divide every term by x, just like that. Whatever the value is, the highest, if this had been a 2, you would have divided by x squared. Okay, so anyway, divide by x, divide by x. I'm just kind of showing you, okay, what that would be, and then of course, that again, this would go, this is 1, right here, this is 0, that limit is 0. You can't do like this on an on an AP calculus test. You've got to carry out the rule. Okay, the answer is 2 in this case here. All right. One more time with this limit here, because I just want to show you, if you, it don't matter what you have, 3 over x squared, this limit is 0. So just kind of keep in mind that that's going to be a limit. This is just going to make it get to 0 quicker because you're squaring it. Even if you raise it to the 4th power, doesn't matter. Okay, this limit's still 0. Okay. All right. Okay, now let's see if that's everything on limits that we're going to look at. All right, let's look at a left and right limit very quickly. I think we're going to end it there, and then we'll look at continuity later. This is the last of our limits, so let's look at it. Let's say sometimes the limit as x approaches 1, and we're talking about, this means from the left. That little symbol means from the left. From the left. Okay, the limit as x approaches 1, that means from the right. From right. Okay. Now, let's look at these, what we got here. Alright, so -1 over x minus 1. Plus 1 or minus 1. It don't matter if it's plus or minus. Minus 1. Okay. we're looking at both the numerator and the denominator. This numerator limit is -1, right? I mean, that's what it is. And this numerator is negative. Negative, yes. Okay. Now, what we're doing here is, let's take this x minus 1 rather, and let's approach it from the left. Okay, from the left of this. Okay, so I can probably plug in, in other words, you know, I can probably plug in, say, like a half. A half minus 1 is -1/2, which is actually 1/2 minus the 1 can be written as anything we want over the same number. So in this case, since we have a 2 as the denominator, this is 2 over 2. Had this been 3, we would have wrote 3 over 3. This is -1/2. -1/2 is negative, isn't it? Obviously. So this limit down here is negative. So a negative divided by a negative is positive. So what that, you know, so that means that, you know, the graph to the left of 1, okay, is going to go up. Okay, and if I had a picture of it, I'd show it to you. But this is positive, okay. Alright, and so that's what you're doing. Just think about this. Numerator's negative. This one right here, you plug in a number to the left of 1, okay. Alright, whatever a is, x minus 1, so plug in a number to the left of 1. And I always like to pick a half. You could have picked a 4th or anything like that. Don't go too far over. Just get real close to 1, okay. Alright, and so negative over negative is positive. So in this case, we're going to say positive infinity. Alright, so that's equal to, well, a negative over negative is positive, but not positive. So let's just say this is positive infinity. We already know this one's going to stay negative all the time, isn't it? Okay. What does it look like to the left of whatever a is? A is 1. Put a number to the left of it. On the number line, here's 1. I just picked, here's 0. I picked a half. So here I'm going to pick, I'm probably going to pick something else to the right of 1, okay? And so that's what's going to happen to the right. So 1.5 or something like that. So let's see here. What's the behavior of a graph? That's what it really is telling us. So to the left of 1, we know the graph is increasing. There is an asymptote, a vertical asymptote at x equals 1. X minus 1 is 0, x equals 1. So a vertical asymptote at 1. The graph is going to, I don't know where it's going to go through, but anyway, it's going to increase. It's going up, probably doing that right there. Now, does it increase, does it go up as we approach it from the right side, from the right, this is from the left here, going this way, it's going increasing, 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 increasing. It's going to positive infinity. This way. Positive infinity. Okay, that's what we're talking about right there. Alright, I have a feeling this one's going to go down right here, and I don't know what it's going to do here, but it's going to shoot down. I think if I had to look at this graph, just thinking about it, I want to say it's doing something like this, and then it's going to do something like that and go down, and this is going to be negative infinity. Let's check it out though. Alright, so from the right, Okay. We got -1 over x minus 1. We're checking from the right. Alright, from the right of a, which is 1. Okay. Alright, so x minus a. Alright, so we're going to check to the right of 1. We're going to probably just try 1.5, which is 3/2. Alright, I could probably put in a 2 right there. Let's see what we got here. We know the top one's negative. Numerator's negative. Now, had this been a positive 1, we would have put a positive sign right here. But since this is -1, we're going to put a negative sign here. All right. There's no x to go with it, so the number itself, the limit at the top, is negative. We could have done the limit as x approaches 1. -1 at the top here, it's just -1. No matter what it is, it's -1. So the answer is -1, which is a negative number. That's all it counts, it is a negative number. Alright, so let's plug in. I did plug in 2. You can, I guess, or 3/2. I'll just go 3/2. 3/2 minus 1, which is 3/2 minus 2/2. Now this is a lot to swallow. That's a positive 1/2. So that's a positive answer. So that's right there. A negative over a positive is negative. So negative infinity is the answer here. So this limit is -infinity. Okay. It gives us an idea of the graph without even drawing the graph. Let me say that facing you. It gives you an idea of the graph without drawing the graph. So this is going to be equal to negative infinity. Okay. And once again, if I don't have my calculator with me, but yes I do. So let's see here. Out of curiosity. Okay, I'm almost through here. I'm trying to finish. Let me get my calculator out right here. And let me clear. Okay. Alright, so -1. Alright. X minus 1. Close parentheses. Graph. And I don't know if you can see that, but okay. Don't show an asymptote here, but I'm sure that there is an asymptote here at 1. Okay. But you see, this is positive infinity to the left of 1. Okay. And I don't know if you can see that. Let me see if you can even see that at all. I'm going to put it right here where you can see the graph. Okay. Whoa, I don't even know if you can see that. Okay, positive infinity to the left of 1, negative infinity to the right of 1. As it approaches 1 from the left, it's going up, higher, 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 forever, upward, positive infinity. To the left of 1, down, 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 negative infinity forever. Okay? And so that's the idea behind that right there. If you were to graph that, that's what you would see. And that's giving you an idea, again, what that graph looks like. Okay, I probably should have reserved this one for another time because it takes some explanation. Okay, I'm going to stop right there because there is continuity after this, and that's going to take an entire, what you might say, a class period, if you will. So anyway, this is part of that big 3 limit. You've seen enough, probably. You know, you can digest this. This is probably just enough to digest. But anyway, KP the Math G getting ready to sign off. I always sign off with a clap. Okay. But before I do that, I'd like to say, if you haven't subscribed, you need to subscribe. But if you don't subscribe, that's okay. I say you need to. You don't have to. I like to see some more subscriptions. But again, it's not for me. It is for you. If you'd like to make a comment about this, please do so. If you'd like to hit the like button, not the unlike button. No. If you hit unlike, please comment and tell me what you didn't like about the video. And that gives me time to kind of think about what I need to do better. Anyway, I'm just glad and happy to be able to do this, and it's for you. Anyway, ladies and gentlemen, this is KP the Math G getting ready to sign off. Ladies and gentlemen, have a great, great day.